Today, we'll be talking about the Hopcroft-Karp algorithm. This algorithm is used for finding a maximal matching bipartite graph. In short, this means finding the best way of linking two separate groups to each other, given their preferences. These two groups could be matching patients to heart donors, or solving scheduling problems between these patients, or any scheduling problem for that matter. However, the most common example given in this day and age is matchmaking problems. For this example, we're going to stick with matching numbers to letters. Each number or letter is linked via various edges, which each represent a preference or compatibility between the two. The solution we are looking for is each number matched to one letter, and each letter to one number. The first step is to make a possible solution by matching each number along the first possible edge. We will represent the current solution by using orange edges. This leads to matching 1 to A, 2 to B, 3 to E, as A is already matched with 1. When we get to 4, the only possible match is to B. However, this is already matched, so we will leave 4 unmatched and come back to it later. We then move on to matching 5, but cannot match 6 as C and E are both already matched. After this first iteration, the only numbers left unmatched are 4 and 6, and the only letters unmatched, D and F. The next step in the algorithm is to do a breadth-first search, starting from the unmatched nodes. To start with, move along the unmatched edges and add these to a separate graph like this. Next, follow the matched edges, the orange ones in this example, to get back to the numbers on the left-hand side. Then move along the unmatched edges, back to the right-hand side. You repeat this alternating between matched and unmatched edges, until you've reached the unmatched nodes on the right hand side, which at this point we have. Now that this graph is constructed, we can find an augmenting path between an unmatched node on the left and right. An augmenting path in this case is one which alternates between blue and orange. To finish this iteration, we simply flip the edges from blue to orange and orange to blue, and update these changes in the original graph. By doing this, you can see that 6 and D have now been matched to other nodes, without unmatching any other nodes. Now we move on to the next iteration, starting at just 4 this time, moving along to B, and B to 2, 2 to D, D to 5, and then to F and C. This highlights an augmenting path between 4 and F, which can then be flipped, leaving no unmatched nodes. Now we have our optimal matching.
Now we will explain the time complexity of the algorithm. Each iteration carries out a breadth-first search taking big O of all edges time. Then a depth-first search, which also takes big O of all edges time. This can be simplified to both searches taking big O of all edges time. After root v iterations, the shortest remaining augmenting path has at least root v edges in it. The algorithm always increases the augmenting path by at least 1, and the size of the partial matching can only differ from the optimal matching by root v. Therefore, we can only further iterate a maximum of root v times before finding an optimal matching. We can simplify this to just big O of root v. Therefore, the worst case scenario would be that the algorithm runs in big O of e root v time. However, it has been shown to only take big O of e log v time for sparse graphs. These are graphs with few edges.